Hello, today we're going to be talking about the photoelectric effect. So the photoelectric effect is when light of sufficient energy shines on the surface of a metal. Electrons can actually be ejected from that metal. So that's why it's called the photoelectric effect, because the photons of light have to hit the metal in order for the electrons to be ejected. Now, I said it has to be of a sufficient energy. So essentially, you have your metal, and when the photons come in, they can hit the electrons that are in that sea of valence electrons that is present in metallic bonding. If the photons have enough energy, then they can actually displace the electron and push it out of the metal. And that's the photoelectric effect. Now, the photoelectric effect is important because it helps us determine the relationship between energy, wavelength, and frequency. And there's two important equations for this. E equals HV. I know it's a Greek letter, but I like to use V just because it looks like a V. And then the other equation is C equals lambda V. E is energy, the V is frequency, and this upside down Y looking thing is lambda, it's wavelength. And then H and C are constants. C is the speed of light and H is Planck's constant. Now, what this means essentially is that it tells you the relationship between those three variables. As energy increases, the frequency increases, and vice versa. But frequency and wavelength are inversely related. As wavelength increases, frequency decreases. So as a result, energy and wavelength are inversely proportional as well. As energy increases, the wavelength decreases. So these equations are given on your formula sheet for AP Chemistry, as are the constants. H is 6.63 times 10 to the negative 34, and C, the speed of light, is 3.0 times 10 to the 8th. So they'll give you the constants in the formulas. You just have to plug in the numbers. So let's do an example of this. What is the energy of an X-ray that has a wavelength of 3.2 times 10 to the negative 9th meters? Please make sure that your wavelength is in meters. It needs to be for that those relationships to work. So the first thing I want to do is use C equals lambda V. So C is the speed of light, 3.0 times 10 to the 8th, and that's in meters per second, which is why your wavelength needs to be in meters as well. Your wavelength is 3.2 times 10 to the negative 9th meters, and we're going to solve for the frequency, and so frequency, when you divide that, is 9.4 times 10 to the 16th. Now the unit here, because of our unit for the speed of light, is actually inverse seconds, or s-1. You also see it sometimes as hertz, which is the same thing as inverse seconds. It's the number of waves that pass a point in a given amount of time. Now that we have frequency, we can plug it into E equals HV. E is the energy, which is what we're looking for. H is Planck's constant, 6.63 times 10 to the negative 34th. And our frequency that we just found, 9.4 times 10 to the 16th. If you multiply those, you'll get the energy, which is 6.2 times 10 to the negative 17th joules. So that's how many joules of energy are in that X-ray.